In this segment, I'd like to talk about conditional probability. Before we define what conditional probability is, let me start with an example. So you roll a fair six-sided die and you record the result. That's the experiment. A is the event that you roll a 4. B is the event that you roll an even number. Okay, if I ask you what's the probability of A, then you'll say, well, all the events are equally likely. There are 6. All the outcomes, rather, are equally likely. A is the set that consists of a single outcome. There are 6 possible outcomes, so the probability of A is 1 out of 6. Okay, and if I wanted the event that you roll an even number, well, what's the how many elements are in B? What's the cardinality of B? That's 2, 4, 6. So there are 3 elements in B, and there are 6 elements in S. So 3 out of 6 is 1/2. Okay, so probability of A is 1/6. Probability of B is 1/2. Now, supposing that I change this a little bit, I say, what probability should you assign to the event that you rolled a particular number? You rolled a 4. A is rolling a 4. What's the probability that you rolled a 4? If I also give you the information, and I haven't let you look at the dice yet, you have to assign the probability because you're going to make a bet or something. Okay, so what probability would you assign to the event that you rolled a 4, given that I guarantee you that you rolled an even number? What's the probability of A given that B has occurred? What number should you give to that? Well, it shouldn't be the same number, right? It shouldn't be the same probability. Let's take a look at another example. You shuffled a standard deck of 52 cards. You pick the first 2 cards from the top of the deck. What's the probability that you got 2 aces? Okay, well, if you think of this in terms of a 2-card hand, as we were discussing previously, right? It's a partition, right? You're taking 52 cards. You're splitting up, right? Each of the cards is distinct, so there are 52 symbols, 52 distinct objects, and you're putting them into 2 piles. In one pile you have 2, in the other pile you have 52 minus 2, 50. And it doesn't matter how you arrange within the pile. We're not concerned about the order. Okay, so what's that in the language we've used before? That's 52 choose 2, right? There are 52 choose 2 2-card hands, and they are all equally likely. That's the number of 2-card hands. And now, how many hands have 2 aces? Well, there are 4 aces, and then you'd have to choose 2 of them to give yourself 2 aces. So there are 4 choose 2 hands, which have 2 aces. There are 52 choose 2 2-card hands of any kind, without any restriction, and they're all equally likely. So 4 choose 2 divided by 52 choose 2. That's just like some problems that we saw recently. Once again, there are 4 choose 2 2-card hands that have 2 aces. There are 52 choose 2 2-card hands, all equally likely. And so the probability of a 2-card hand with 2 aces is 4 choose 2 divided by 52 choose 2. Right? So if I asked you, what is the probability of getting 2 aces? The dealer, you take 2 cards off the top of a fairly shuffled deck, or the dealer throws 2 cards at you, what's the probability that you have 2 aces? Well, it's this number. Okay. Now, what if I said, what's the probability of getting 2 aces? And I'll tell you that the first card that you got is a king. What's the probability of getting 2 aces? Okay. Well, it's 0 now. Whatever the second card is, you don't have 2 aces. So you've only got 2 cards on one of them. One of them is a king. Okay, so that information, right? The number, when we assign this probability, we assigned a different probability than when we didn't have that piece of information, that the first card is a king. Okay, so conditional probability helps us deal with situations like that. Okay. So conditional probability, these are probabilities of events given that some event has occurred. So we use the notation, this is read as the probability of the event A given B. So A and B are events, the probability of A given B. That's an example of a conditional probability. Okay, so in our case, the probability of A given B, going back to our example, is 0. Okay, now how do we calculate those? The probability of A given B is defined to be the probability of A intersection B divided by the probability of B, and you never want to be dividing by 0, so provided that the probability of B is not equal to 0. And that is the definition. Okay. All right, so let's do an example. Supposing that we are given adult literacy rates in Pakistan. So we're told that the male adult literacy rate is 66.25%, and that the female literacy rate is 41.75%. And we're given that. And now we're asked that give me the probability that an adult Pakistani is both literate and male. Okay, that's the question. Okay, so we were given certain pieces of information. Let's label them as events. Okay, so let L be the event that a particular Pakistani is literate. Let M be the event that an adult Pakistani is male. Let F be the event that an adult Pakistani is female. What did the minister, in this example, the minister was giving the statistics. So the minister told us that the probability that an adult Pakistani is literate, given that they are male, is 0.6625. And the other piece of information that the minister gave us was that the probability that an adult Pakistani is literate, given that they are female, is 0.4175. And what are we looking for? Right. What we're looking for is that an adult Pakistani is literate and male. And that's the probability of L intersection N, right? L was the event that adult Pakistani was literate. M was the event that the adult adult Pakistani is male. Okay. Now, if we want to use these numbers, right, we want the probability of, we might need the probability of M and the probability of F. Okay, that we weren't given, so we need those. Okay, so if you look at the country studies book, we find that there are 111 men for every 100 women, according to an American country study. So we can write that the probability that an adult Pakistani is male is 111 out of 111 plus 100, and that's 0.5261. And similarly for female, the probability that an adult Pakistani is female is 100 over 111 plus 100. That's equal to 0.4739. Okay, so now let's see if we have enough information to do the problem. Okay. The probability that an adult Pakistani is literate, given that they are male, that conditional probability is by definition the probability of L intersection M divided by the probability of M. Okay. And the probability of L intersection M is what we are trying to find. And we have information for the probability of L given M and the probability of M. So we worked out the probability of L intersection M. Well, we were given that is 0.6625. And we worked out that the probability that an adult Pakistani is male was 0.5261. Okay. So now the probability of L intersection M is 0.6625 times 0.5261, and that works out to 0.3485. The one important thing that comes up here is the idea of an independent event. So I'll give you the definition. Events A and B are independent if the probability of A intersection B is equal to the probability of A times the probability of B. Now, not all events are independent. Don't use this formula unless you know that A and B are independent events. Okay. Now, what's the result of that? Well, if A and B are independent and the probability of B is not equal to 0, then the probability of A given B, well, what was that? By definition, that was the probability of A intersection B divided by the probability of B. That's equal to, if they're independent, the probability of A times the probability of B divided by the probability of B, and then the probabilities of B cancel each other out. So in the special case of A and B being independent events, then the probability of A given B is just the probability of A. Similarly, another result would be that if A and B are independent and the probability of A is not equal to 0, then the probability of B given A is equal to the probability of B. All right, so let's do an example. Supposing that you have 2 fair die, and you're going to roll each one once, and the results are recorded as ordered pairs. Okay, so that's the experiment. Let A be the event that the first die gives a 1. Let B be the event that the second die gives a 2. Are A and B independent? Instinctively, without doing any calculations, what do you think? Okay. Well, all right, now let's do the calculation. Okay, so the probability of A, remember, A is the first die gives a 1, B is the second die gives a 2. The probability of rolling a 1 is 1/6, fair die. The probability of rolling a 2 is 1 out of 6. Okay. Okay, so there are 36 ordered pairs. Each one is equally likely. So the probability of A and B is a probability that the first one rolls a 1 and the next one rolls a 2. And that's 1 out of 36. And that's in fact equal to the probability of A, which was 1/6, times the probability of B, which is 1/6. So A and B are independent. Okay, dependent events. If it turns out that two events are not independent, then we say they're dependent. Okay. Now, be a little bit careful here. I've seen often that there's a confusion of students. They forget the definitions or they mix up the definitions. Independent is not the same thing as mutually exclusive. Okay. Independent will imply that the probability of A given B is equal to probability of A, and the probability of B given A is equal to probability of B. But mutually exclusive means the probability of A given B, right? Mutually exclusive means that the intersections are 0, and then that for conditional probabilities, that will imply that the probability of A given B is 0. If you're given that B has occurred, that means that A cannot occur. So the probability of A intersection B would be 0. And then the probability of A given B would be 0. A multiplicative rule is useful here in some problems. And let's lay that out. The probability of A intersection B, if you want to write that in terms of a conditional probability, that's equal to the probability of A times the probability of B given A. And the probability of A and B can also be written as the probability of B times the probability of A given B. Okay, you can get these results just by manipulating the definition of conditional probability. Now, if you wanted to do this for 3 events, you would get that the probability of A intersection B intersection C is the probability of B times the probability of B given A times the probability of C given A intersection B. Okay. And you should work this out for more than 3 events. You have to play around a little bit, right? You would manipulate the definitions. And what you will get is that the probability of E1 intersection E2 and so on up to intersection En, that's the probability of E1 times the probability of E2 given E1 times the probability of E3 given E1 intersection E2, and so on up to the probability of En given E1 intersection E2 up to intersection En minus 1. Now let's actually use that. Supposing we have 3 black and 7 white socks in a drawer. We select one at random and we don't replace it. Then we select a second one at random. Okay. Let's say A is the event that the first sock is black. B is the event that the second sock is white. Okay. Show that the probability of A is 3 out of 10. Okay. Now let's just think about it. There were 10 socks. 3 of them were black. So if we randomly select one of them, we could pick any one of three. And we're assuming here that the selection of each sock is equally likely. So from what we've discussed before, it's 3 out of the total number of socks, 3 out of 10. Okay, the probability of B given A is 2 out of 9. Okay. Probability of B given A is 2 out of 9. Okay, why is that? Well, you're given A, so you know that the first sock was black. Okay, A is the event, the first sock is black. So now there are 9 socks left, and 7 of them are white. So the probability that on the second selection of a sock, now given that a black sock was taken out, now there are 7 white socks left out of 9 total socks. So the probability of drawing a white sock is 7. The probability of the probability of drawing a should be 7 out of 9. Sorry, I read 2 out of 9. Not sure. 7 out of 9. And now you can use the multiplication rule. What was the multiplication rule? The multiplication rule is that the probability of A intersection B is the probability of A times the probability of B intersection B given A. And then you should be able to work out what the probability of A intersection B is in this case. You have enough information to do that. Okay. So now let's try a few examples. Okay. You have 2 cards drawn at random from a standard fair, well-shuffled 52-card deck without replacement. What's the probability of drawing 2 cards of the same suit, given that the first card drawn is the King of Hearts? Okay, let's see if we can think our way through this one. The first card drawn is the King of Hearts. So we've got 51 cards left, and we have to draw a heart card. And we've removed 1 heart. So there are 12 heart cards out of 51 cards. All the cards can be equally likely. So we'd suspect that the probability is 12 out of 51. Okay. The family has a younger child and an older child. What's the probability that a younger child is a girl? That the younger child is a girl? What do you think? What's the probability that the younger child is a girl, given that at least one of the 2 children is a girl? Let's assume an equal probability of a boy or a girl being there. Unless there's some, it turns out that unless there's some external interference, there's slightly more boys. 104, 105 boys are born per 100 girls. But in our simplified thought experiment world, let's say there's an equal probability of a boy or a girl being born. Well, I would say the probability that the younger child is a girl is a half. Right? That's what we were given in the here. Equal probability of boy or girl being born. What's the probability that the younger child is a girl, given that at least one of the 2 children is a girl? Okay. Well, what are all the possibilities? There were boy, 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 girl, girl, boy, girl, girl. Now, so what do we have? So the boy, boy is excluded. So that should actually change the probability. Sounds like it should change the probability for you. Okay. So you should think about that. Okay. So if we list, in simple cases, you can just list all the elements of the set S. So boy and then a boy, boy and then a girl, girl and then a boy, girl and then a girl. So all the outcomes are equally likely. So if you just ask about the probability that the younger child is a girl, that's this one and this one. So half. Let A be the event that the second child is a girl. So A is boy, girl, or girl, girl. And let B the event that at least one of the two is a girl. Then that's boy, girl, girl, boy, and girl, girl. And if you're doing probability of A given B, that's what we're being asked for, then we need probability of A intersection B. So any intersection of B is boy, girl, girl, girl. Then the probability of A intersection B, that's 2 elements out of equally likely out of 4 elements, so 2 out of 4. And the probability of B is 3 elements out of 4 equally likely elements, that's 3 out of 4. So then the result is 2 out of 4 divided by 3 out of 4 is 2 out of 3. Okay. So in the next session, we will continue to look at conditional probability.